Hi, Paige. I circled the ones that you asked for, and I am going to try to remember your last question about the ratios. But I'll just kind of go through, draw an example for each of these, and then I highlighted in pink the ones that you said you were having extra trouble with. So hopefully this helps. All right, so first here, I am starting with x is greater than y. I can do a whole bunch of stuff to this equation. It looks like here they added 50 to both sides, so that's fine. I can add 50 to any inequality. Whoops, at 50. And then my inequality direction stays the same. Oh, but wait, actually, I need to go back a step because they didn't add 50 right away. They did a couple things here. So first, it looks like they multiplied x and y by a -1. That's how they got minus x and minus y. So let's see, if I multiply everything in this equation by -1, I'm going to have negative x, I'm going to have negative y, but because it's a negative, it switches directions. Then I'll go and add 50 to both sides, and I can write it out in front. So I have 50 minus x and 50 minus y, and my inequality now, when I add the 50, just stays the same. And so this one is, in fact, true. I think the one we did in our homework, the inequality direction was the other way around, which meant the one in the homework was false. All right, let's see, for number 4 here, well, what did they do is they divided both sides by -3, but when I divide by a negative, the direction of my inequality changes, and then everything else just is the same as equations. So I get x, I get +4, but the direction switches to less than, and so this one is also true. All right, if the corresponding angles of two polygons are congruent, then the polygons are similar. So we've talked a little bit about polygons being similar together. We didn't talk a ton about them. But this one, I'm going to try to think if I can make an example that works and make an example that doesn't. Well, this is polygons, but I'm going to make it easy, and I'm going to go and start maybe with triangles. If I start with triangles, I actually am always going to get them to be similar. So let's move on to rectangles, or sorry, quadrilaterals. I have angles that are congruent. So, for example, my nice easy example here would be if I had a square. All right, so really I have angle 1, angle 2, angle 3, and angle 4. And then I want to draw another shape that has 4 right angles, but is not just this blown up, right? So I can definitely do the same where those are similar. So that's kind of my yes case. But can I draw it where they're not? Well, yeah, because I can just draw a long, long rectangle like that. Now all 4 angles are in fact the same, but these are definitely not similar. Our definition for similar was about the sides being in proportion. So like basically if this were 2 and this were 2, I have some scale factor. Let's say I multiply both sides by 3. I would want 6 and 6, but obviously this would be kind of an example where that wasn't true. If 2 polygons are congruent, then they are similar. Well, that is going to be true because it just means the scale factor is 1. I didn't blow it up or shrink it down at all. I just took my picture and I copied it over exactly. That does actually count as being similar. All right, and then number 20 here. So the thing about number 20, I mean, you kind of want to think about all of them, but here, right triangles, well, that's talking about the angles, and scalene is talking about the sides. So let's see, can I draw a right triangle that is also scalene? Well, I definitely can. So there we go. I have a right triangle, and then being similar to a scalene triangle would just be taking this one and blowing it up or shrinking it down. Let's shrink it down here for size. So these two, maybe if I'm labeling them, I call this one right, I call this one scalene, but that's my yes case. Now, let's think about another one. If I had a right triangle that was a special right triangle because it was right and isosceles, now this one and that one are a no. So I can make it happen. I don't have to. That means that it's going to be sometimes. All right, so on this picture here, we have a couple of things going on. For question 21, this, there was a typo. As 21 is written, you can't do it. So you were right in saying, how the heck do you know the length of AD and DC? I thought I had fixed it, but maybe I didn't. This is supposed to be AC, but as it's written, you don't know anything. You would just say can't be determined as it's written. If it were instead AC, whoops, not like that, sorry. I wanted AD. Oh, shoot. I'm messing myself up here. Sorry. I'm trying to look at Miss Mather's answer key where she kind of fixed it, but she wrote it the other way around. You actually can answer this one. I did fix it before I sent it out to you. What's AC? AC is my entire side. What's AD? AD is just a part of the entire side. We also know that we can make up AC with segment addition postulate with these two pieces. The whole is always bigger than one of the parts. That means AC is always going to be the greater number. So in this case, AD is going to be less than. You don't need to actually know the numbers. But I think you got mixed up because I think you were combining mine and the one that Miss Mather did, because your question on your email said AD and DC. So just be careful with what it looks like, but I made sure the quiz is good, so the quiz will be very clear about which ones. All right, and then lastly here we have BAC and 70. So what I'm going to look at for this one is I'm going to look at my entire triangle. But before I do that, I do in fact know that up here is 40, so I might start with that. I do know over here is 110 because this is a straight line. And now, let's see. So I might start out by saying, okay, well, BAC is this angle here, so maybe I want to look at the whole thing, but I don't know anything about 70, and I don't know what this is down here, and I don't know what this angle is here, so I actually need to go backwards and think about something else. Yeah. So what I'm going to look at is this triangle, and this triangle here, I want to think about what these angles down here can be. Well, I have 110, so I know, maybe I label it, I'll just call it angle 1 and angle 2. I know that the measure of 1 plus the measure of 2 is going to add up to 70. Oh, and look, I'm comparing BAC, which was 1, with 70. That's my part. 70 is my whole, and so BAC must be less than 70. All right, and then these last couple ones. So when you are doing these questions, first of all, draw yourself a picture. So I have the measures of a hexagon. So I'm going to draw a 6-sided shape. I don't really care if it's accurate or not. There we go. And then I'm going to just label my angles inside of here. I don't know what they actually are, but what I know is that they're going to be in order. And I know the sum of the angles of a hexagon. So first of all, my sum of the interior angles is going to be 720. And I did that by doing 4 times 180. I got 4 because I did 6 minus 2. I'm going to label them with 4x and 5x and 5x, and make sure you go in order here. Whoops, and 8x and 9x and 9x. And I don't know my multiplier. That's what I'm trying to find first. So I'm going to add all of these up, and I get 40x is 720. And I divide, and I get that x is 18. So 18 is my multiplier. So I've got to go in. If I wanted all these angles, I would want to multiply each thing by 18. But they asked me here for the smallest exterior angle. So what I'm thinking about inside is I'm thinking about extending one of my sides out like this, and then my exterior angle, whoops, being this angle right in here. Well, if I want the smallest exterior angle, that's going to be matched with the biggest interior angle. The largest interior angle is the 9, whatever, the 9 times my multiplier. So that's going to give me 162. If I'm looking at this here, if this is 162, then what's left over must add up to 180. So my exterior angle is going to be 18. It just happens that it's the same as x. You do want to go through all the work. All right, parallelogram. Well, I'm going to draw my parallelogram. And what do I know about this parallelogram? I know that the sides are in the ratio of 4 to 7. I'll try to draw that in order here. So that's going to be like my smaller side is 4 times some multiplier. My longer side is 7 times some multiplier. But it's a parallelogram, so I know those opposite sides are the same. All right, perimeter, I'm going to add up all 4 sides here. So let's see, I have 2 sides of 4 and I have 2 sides of 7, and I'm going to add up and be 150. That's going to give me 22x is 150. I need to divide by 22. And when I started this problem the first time, I went off on the side and I did 150 divided by 22, and I got some gross decimal. So don't do that. Just keep it as a fraction and just simplify it. Let's see, I know that 2 goes into both. So I'll start with 2. That's going to give me 75 over 11. 11 is prime, and it doesn't go into 75. So this is my multiplier. Now I wanted to find the lengths of the sides, which means I just have to multiply 4 times 75 elevenths. I'll put it as 4 over 1. And I need to multiply 7 times 75 elevenths. All right, so let's see, 4 times 75 is going to give me 300. That's 300 elevenths, one of my sides. 7, let's see, I have 3/4, and I have 7 of them. That's going to be $5.25. So that's 525 over 11. Those are my side lengths. All right, kind of switching gears here for 31 and 32. The lengths of 2 sides of a triangle are m and m plus 4. And I want to know the length of the third side. So I'm going to think about m and m plus 4 in kind of 2 different colors here. So let me highlight. Let's think about m as green, and then m plus 4 will be in pink. And I'm going to put these together to make a triangle. Well, because m is the same, my longer side, m plus 4, is going to be like this. And now my shorter side, m, I don't know exactly how long it is, but I'm going to imagine taking this and kind of moving it around to make different triangles. If I take this and make the smallest triangle that I absolutely can, I mean, I can't even see it here, but you can kind of imagine it. Well, what is my length of this third side that's going to connect these two? In this case, 4, it can't be exactly 4 because that would mean that my green was sitting exactly on top of the pink. But if it's like a minuscule above, I can have 4 as my lower bound. So it's not or equal, it's just less than. All right, and then my other kind of case here with my green line is the biggest triangle I could possibly imagine. So I'm going to take it, and I'm not going to stretch it all the way straight because that's not a triangle. So I'm just going to stretch it ever so slightly up like that. Whoops, sorry about that. And when I connect, what is that length going to be? Well, it can't be m plus 4, but that's going to be kind of my max. I can be ever so slightly smaller than that, so it will be 2m plus 4. So I'm going to be in between 4 and 2m plus 4. That's kind of how you want to think about it for each one. All right, and then our ratio here, you want to express the ratio of the height to the base. Well, height to base means I'm going to have h over b. The only problem with this one is that they're not being measured in the same thing, so you have to change them. I probably would change my, I don't know, let's change meters into millimeters. So 0.2 meters. First, I'm going to change into centimeters. I know that 1 meter is equal to 100 centimeters. So we haven't talked really about this, but what I would do is some dimensional analysis. 0.2 meters over 1, and I'm going to multiply by a fraction, and I want my meters to cancel out. So I'm actually going to multiply by 100 over 1. I'm just taking this and putting it in a fraction. My units cancel, and I'm left with, well, 0.2 times 100 is going to give me 20 centimeters. And then I'll do the same thing to change it into millimeters. I'll do 20 centimeters over 1 times, this time, it's going to be that 1 centimeter is equal to 10 millimeters. My centimeters cancel, and I get 200 millimeters. I need to do that first. So now I can compare. Let's see. My height was 40 millimeters. My base is now 200 millimeters. Millimeters is gone. That's the point. That's why you want them together, so that you can just get a ratio with numbers. I get 4 over 20. 4 goes into 4 once, into 25 times, which gives me that ratio of 1 to 5. All right, and then your ratio and number question, I think you're kind of referring to solving questions kind of like 36. If you know, how do you find the numbers of the ratio if you are just given the number and the ratio? So you kind of have to know what's what. So like here, I could have, let's highlight our information. Well, 12 and 15 are both in between the 2 hash and the right angle. And then in another color, maybe have y and 12. And then you can set up a whole bunch of different proportions to solve for y here. So I think this is kind of getting at what you're saying, maybe kind of like 35 instead. But hopefully this answers, just let me know if it doesn't. All right, so I could do the blue to the blue equals the green to the green. Just make sure that when I did blue to blue, I had like my left-hand one on the top and my right-hand one on the bottom. So basically, you just want to be consistent. Or you could have compared blue to green in one triangle to blue to green in the other triangle. You could have compared green to blue in one triangle and green to blue. Well, that's just that one flipped over. You could have compared, I think that's pretty much it. I guess you could flip this one around too. Yeah, so I think that's kind of what you're saying. Let me know if you still have a question on that. Hopefully this helps. See you soon.